Hello, I Anand Jain from Hanumangarh, Rajasthan welcomes you to Shridevi Classes YouTube channel where we inculcate interest and confidence in science and engineering subject. Today in our class 12th physics playlist in chapter electromagnetism, we will study magnetic field on the axis of a current carrying coil and understand how magnetic field flux density decreases as we increase axial distance from center of coil. And for exam preparation, we will also solve some numerical. Let's start. First, derive expression for magnetic field on the axis of a current carrying coil, and for that we have given a coil of n turns and a radius, and we place that coil in YZ plane with the center of coil on origin and axis of coil along x direction. Now when this coil carries I current, it produces magnetic field on its axis, so we have to find out magnetic field at different positions on axis with certain axial distance from center. Let we have an observation position P on axis at a axial distance x from center of coil. To find out resultant magnetic field contribution of this entire n-turn coil carrying I current, we'll take a small current elemental length at position M, and as per Biot-Savart, the elemental magnetic field flux density contribution at P by elemental current length at position M is given as mu 0 I delta L sin theta upon 4 pi r square, where theta is angle between current element and this position vector r of observation point, and this angle, as coil is in YZ plane and this position is on x-axis, this angle become 90 degree and sin 90 become 1, and our numerator expression gets simplified. This small r is distance of observation position from elemental current length placed at position M from coil. As per Maxwell right hand corkscrew rule, the direction of elemental magnetic field contribution by M position current element at position P is perpendicular to the plane which contain current element as shown by red arrow, and position vector connecting observation position P from source current element as shown by this blue arrow or this plane. As per Maxwell right hand rule, when thumb is pointing in the direction of current, this tip of curled finger at this position perpendicular to this plane of current element and position vector represent this direction of elemental magnetic field flux density contribution. Now for mathematical manipulation, we can resolve this magnetic field component, one along axis of coil, that is x direction, delta B of M point in x direction, and one perpendicular to this axial direction in YZ plane, and this component will become delta B M Y. We have obtained elemental magnetic field flux density contribution at observation position P by a small elemental current length at position M, and to find out resultant magnetic field flux density at this observation position P by the entire current carrying n turns of this coil, let's use symmetry of this coil current distribution with respect to observation position and choose another elemental current length at position N which is on periphery just diametrical opposite to M, and let's find out elemental magnetic field flux density contribution at point P by this current elemental length of position N, and as per Biot-Savart law, this is again mu 0 I delta L sin theta upon 4 pi r square, where theta is angle between current element and this position vector r which is 90, and sin 90 become 1, and this r is the same radial distance of observation position P from periphery of coil as it is with M position current element or N position of current element. Now the direction of this elemental magnetic field flux density contribution is obtained by Maxwell right hand corkscrew rule and Maxwell right hand thumb rule. The direction of magnetic field flux density contribution must be perpendicular to the plane of current as shown by red arrow, and distance vector joining observation position P from position of current element, this plane perpendicular to this plane. The elemental magnetic field flux density contribution is indicated by this tip of curled finger at this position P when the thumb of right hand are directed in the direction of current in elemental length. So this would be the direction of elemental magnetic field flux density contribution by elemental length positioned at N point on coil periphery symmetrically opposite to M position. Now this elemental magnetic flux density contribution of N position elemental length can also be resolved in two components, one along axis of coil in x direction delta B N x, and second perpendicular to this axis in YZ plane delta B N Y. Now if we check the symmetry, the distance of observation position from periphery position of M and N is the same, so the two magnitude are same. This symmetrical center axis of coil bisect these two elemental magnetic flux density. So the angle formed here of delta Bm with x-axis and delta Bn with x-axis is the same. Let this angle at point P between axial line of coil and position vector r is theta. The elemental magnetic flux density contribution is perpendicular to position vector r, and this yz plane line is perpendicular to x-axis. So this theta and this theta is same. Similarly, due to symmetry, this is also theta. So the two resolve component of elemental magnetic flux density of symmetrical opposite m and n position elemental length got identical y component in yz plane, and the two are just opposite two, so they will neutralize each other, and their axial component come in the same direction. So this vector summation become a simple algebraic manipulation, since for this complete circular coil every elemental length got diametrical opposite symmetrical elemental length, and due to symmetry the magnetic field contribution of those two elemental length when resolved in x direction will add together, and when resolved in yz plane will cancel each other. So all component which are in yz plane for symmetrical opposite pairs become equal and opposite and neutralize each other. So resultant magnetic field flux density of this entire current carrying coil on axis become simple algebraic summation of their axial component. The elemental magnetic field flux density contribution of m positioned elemental length is this and n position current length is this. Due to symmetry, both have same magnitude mu 0 I delta L upon 4 pi r square, and both have the same angle from yz plane equal to this theta. Due to symmetrical position of this observation point with respect to current in circular coil, other elemental length also produce magnetic field of same magnitude with same angle with yz plane, and if we connect tip of all those magnetic field contribution, they will form a cone as shown here, and axial component of all those elemental contribution become, if this angle is theta, then sin theta component, and their summation of all x component by integration become resultant magnetic field of this entire coil. X-axis component is sin theta component of elemental magnetic flux density contribution, and integration of all those x component will give us resultant magnetic field on axis of this coil at x distance from center. Now due to symmetry, along with mu 0 I, this sin theta and distance r all are constant. They brought out of integration as constant, and integration become only integration of circular coil length, and for a coil of a radius and n turns, this entire length become one circumference got 2 pi a length, and turns will have n 2 pi a length, and simplification will make a square in numerator, and this 4 pi get cancel out by 2 pi, and denominator got only 2, and this r square become r cube, and this become our relation mu 0 n I upon a square upon 2 r cube, where n is number of turns in circular coil, I is current flowing in circular coil, a is radius of this coil, and r is distance of observation position from elemental length position, and this can be obtained by Pythagoras calculation of coil radius and axial distance x. In this triangle, r square is summation of a square plus x square, so in place of r cube we can write 3 by 2 root of a square plus x square, and when we study this relation of axial magnetic field, here n, I, radius of coil all are constant. The only variable is distance from center on axis of observation position P, and for minimum value of x, that is at center position of this circular coil on its own plane, x is 0, and when we place x 0, we'll get magnetic field the same as we have obtained earlier, mu 0 n I upon 2 r or 2 a Tesla, and this is the maximum value of magnetic field produced by coil at anywhere in its vicinity. And in coil plane, though the center magnitude is maximum mu 0 n I upon 2a, but on the same plane when we move towards peripheral position, the decrease in magnetic field is small, and everywhere on the plane magnetic field direction is perpendicular to coil plane given by thumb of right hand when finger are curled along the direction of current. Now mathematical analysis of this relation indicates that for small values of x, the decrease of axial magnetic field flux density of current carrying coil is small, but as as we increase axial distance to both sides of this coil from coil plane, the rate of decrease of magnetic field flux density with axial distance increases. This rate of change become maximum and constant at axial distance equal to half of radius, and then again its curvature changes, and for a position very far away from coil center, x is large compared to radius of coil. In place of this summation a square plus x square, we can neglect small radius square component a square, and this become x cube, and simplified magnetic field flux density on axis at a very far away point will become this expression. This indicates that magnetic field flux density is inverse of cube of the distance from axis of the current carrying coil, and this expression is just identical to magnetic field produced by a bar magnet, which also is 1 over x cube proportional relation. Such variation of magnetic field flux density with axial distance for far away points is a hyperbolic variation. For a coil of n turns and a radius, the magnetic field flux density on its axial distance x by current I is given by this expression, and this clearly indicates that as x increases to any side of coil, the magnetic field flux density decreases, and for x equal to 0 at center, magnetic field flux density is maximum mu 0 ni upon 2a, and for small distances from center, the rate of change of magnetic field flux density with axial distance is small, but the rate of change increases continuously, and it becomes maximum and constant at axial distance equal to half of radius, and after that once again the rate of change of magnetic field flux density with displacement change its curvature, and it decrease continuously its magnitude. So dB by dx, rate of change of field flux density with axial displacement, is the maximum and constant at axial distance equal to half of radius, and change of b with x curve change its curvature around this position. So these changing points are known as point of inflection, and they have maximum and steady rate of change of axial field flux density with a displacement. Now these 2 points at both sides of coil axis at half of radius position got maximum rate of change of field flux density with axial displacement, and these points are known as point of inflection. For axial magnetic field of current carrying coil, in our competitive exams, questions are asked on point of inflection, which is at axial distance equal to half of radius at point of inflection. The variation of magnetic field flux density on axis with displacement got maximum and steady rate of change. So dB by dx is not only constant, but it's also maximum, and for this maximum condition, the second derivative of magnetic field flux density on axis with displacement becomes 0. So at point of inflection, dB by dx is constant and maximum, and the second derivative of b with x becomes 0, and this position occurs at both sides of coil at axial distance equal to half of radius. In this expression of magnetic field flux density on axis, if in place of axial distance for point of inflection we place half of radius, and this square become a square by 4, and summation become 5 by 4 a square, and 3 by 2 power of a square make it a cube, and with simplification it become only a. With this 2 it is 2a, and the remaining mu 0 ni upon 2a is nothing but magnetic field at the center of this coil, which is the maximum magnetic field produced by current carrying coil at center, and this 4 denomination in denominator come to numerator with 3 by 2 power 4 root 4, and root 4 is 2, so it become 8, and at denominator we have 5 root 5. Now this 8 upon 5 root 5 can be simplified as 0.716. So magnetic field flux density at point of inflection become 71.6% of maximum magnetic field flux density at center of coil in coil plane. Magnetic field of a current carrying coil is maximum at its center, and as we move to both sides of it on axis, magnetic field flux density decreases in a typical manner, and at an axial distance equal to half of radius, magnetic field flux density changes with respect to displacement at maximum and steady rate, and this point is known as point of inflection. And this property of point of inflection, maximum and constant dB by dx, is used to produce constant magnetic field, and this combination of two two coils known as Helmholtz coil is done in such a way that both coils identical in turns and radius are placed on the same axis with plane parallel to each other with their axial distance equal to their radius, and current is flowing in those coils in such a way that magnetic field of both act in the same direction and add with each other. Each coil got 2 points of inflection at two sides of it. So for this combination of two coils there would be 3 points of inflection, and at this middle point the magnetic field of one coil as we move away from it decreases, and of another coil to which we are coming closer increases with the same amount. So the total amount of magnetic field become constant, and this configuration of two coaxial cable with axial distance equal to radius of identical turns and radius is known as Helmholtz coil, and it is used to produce constant magnetic field in a close vicinity at these middle positions. This example is very important from our examination preparation point of view. In this example it is given that in the earth magnetic field there exists a neutral point where resultant magnetic field of earth magnetic field and other source magnetic field become 0. So such neutral point is obtained at a center of a vertical current carrying coil of radius 10 cm, and this coil is placed in east-west plane so that this coil itself produces its magnetic field in south direction equal and opposite to earth magnetic field in north direction. Now in this same coil if current is made 8 times, then we have to find out position of neutral point on the axis of coil. So we know that at neutral point the resultant magnetic field is 0. That means the magnetic field of coil produced in the direction of north to south and horizontal component of earth magnetic field directed from south to north both are equal and opposite. So we can say magnetic field at the center of coil become equal to horizontal component of earth magnetic field. Now at center coil produce maximum magnetic field, and that maximum magnetic field is equal to earth horizontal component. Now when we increase current in coil turns by 8 times, its magnetic field proportional to current carried by the coil become 8 times at center, and as we move away from center on axis the magnitude of magnetic field decreases and it become 1/8 of central value at certain distance, and we have to find out that axial distance where the center magnetic field which become 8 times reduced to earlier value or equal to earth horizontal component, so that magnetic neutral position will occur at that position, and we have to find out that axial distance where new neutral point will exist. For a current carrying circular coil of n turns and a radius, the magnetic field on axis is given by this expression at axial distance x from center. Now if this axial distance is given in terms of a multiplier of coil radius as x is equal to ma, then in place of x square when we put m square a square and brought that common, then at denominator the a cube get cancelled out by a square of numerator and we got a in denominator, and now this mu 0 ni upon 2a become magnetic field of same circular coil at its center position. We call it B naught. So in terms of center magnetic field flux density B naught and axial distance as a multiple of coil radius m, we can write axial magnetic field as B naught divided by 1 plus m square raised to power 3 by 2. When the coil current is made 8 times, this center value become 8 times, and at certain axial distance equal to ma, the magnetic field become previous axial value, and magnetic neutrality will again occur at certain axial distance equal to ma, and we can find out that value of m is B naught get cancel out, and 1 plus m square raised to power 3 by 2 become 8. 8 is 2 raised to power cube, and when we take cube root, the square root of 1 plus m square become 2, or 1 plus m square become square of 2 or 4. M square become 4 minus 1 3, or m become root 3. So our axial distance when coil radius is 10 centimeter is 10 root 3 centimeter, and at this distance position with 8 times current, the magnetic field on axis become equal to horizontal component of earth magnetic field, and we got neutral position. In our examination, axial magnetic field of current carrying coil and its center value of magnetic field got some typical examination pattern, and we can practice those all possible patterns by simple exercise. In place of axial distance, we can write some multiple m of radius, and when this a square is brought common and 3 by 2 power of it is taken, a cube will become simplified with a naught as a and mu 0 ni upon 2a become magnetic field at center of coil, and axial magnetic field at x is equal to ma distance become this b naught divided by 1 plus m square raised to power 3 by 2, and our axial distance may be 1a, that means m is 1, so 1 and 1 become 2 and this become 2 root 2, and axial magnetic field become 1 by 2 root 2 times of center value, and when m is root 2 and axial distance is root 2a, then root 2 square is 2, 2 and 1 summation become 3, and axial magnetic field will become 1 by 3 root 3 times of center value. Similarly, for x is equal to root 3a value, when m is root 3, this m square become 3, 3 and 1 become 4, and denominator 4 root 4 become 8, and our magnetic field on axis become 1/8 of central value. And similarly, for 2 times of radius distance, 2 square become 4, and this magnetic field become b naught by 5 root 5. With this very useful informative learning video, you could derive expression of resultant magnetic field on the axis of a current carrying coil, and you can also solve probable examination questions, whether they are theoretical or numerical, and you also answer what is Helmholtz coils. Our other learning video of the same playlist are equally useful. You can use them in your studies and share them with your friends. And you could also join our online doubt clearing classes by joining the membership of our YouTube channel by pressing join button just beneath. We wish you all success in your examinations. Happy learning. Thank you very much.